We begin Chapter 5, where we're going to discuss number theory and the real number system. To begin, I'd like to point out the set of natural numbers, often denoted just capital N, are just all the positive integers. So notice it starts at 1, continues to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and as we can see in the ... that means it just continues in that pattern out to infinity. So the next number would be 12, 13, 14, etc. Now it's important to know the natural numbers because some of our problems will use them in the description. For instance, here it says find all the natural number factors. So it's important to know what a natural number is. So it's just find all the natural number factors of each number. Factors means numbers that divide into the number evenly with no remainder. So for instance, 8 is a factor of 16, and one way you might see that written is that 8 vertical bar means divides 16. This is notation the book uses, so you'll see this kind of notation in the homework. I'm not going to particularly use it on our quizzes or exams, but I just wanted to let everybody know that's what the 8 vertical bar 16 means. So we're asking ourselves, what are all the natural numbers that would divide into another number? So first of all, if we're trying to find the natural number factors of 10, we know it's not going to include any numbers larger than 10. So whenever you're looking for the natural number factors, you always look at the number and then smaller than it. And it happens that these natural numbers come in pairs. In order to divide a number, it has to be multiplied by some other number. So for instance, what you would do is you would get your calculator and you would take the number you were given and you would just divide that by 1. And notice we get just an integer, nothing left over, so that means 1 is a factor and its pair is 10. So both 1 and 10 divide 10. And then I keep going to the list. So next I check 2. 10 divided by 2. Yeah, 2 does. And it's paired with the factor pair 5. Okay, so we've checked out 2. Next we go to 3. Is 10 divisible by 3? And notice here we have these decimals. That means it's not divisible perfectly. So you could divide it and get a remainder, but we want perfect division, so 3 is out. And then we check next is 4, and we're just going to do this for all the values. Again, we get a decimal, so that doesn't count either. And then 10 next comes up as 5. Yeah, it divides, but notice we already had 5 in the list. So if you go through this in this orderly fashion, once you start to repeat factors that you've already written down as the pair to earlier value, that's when you know you can stop. So all the natural number factors of 10 are just 1, 2, 5, and 10. So as long as you're patient and you go through it in an orderly way, you can find all the natural number factors. So for instance, 32, you know you're not going to be looking at 33, 34, or anything past 32. So you're going to start at 1. And we know that every number is divisible by 1. And what is it divisible into? Exactly 32 times. So I kind of write them spaced off. And then I go to the next number, 2. With my calculator, yeah, divides into 2 exactly how many times? 16. And then we just continue the process. Here I got a decimal, so that doesn't count. Next is 4. 4 works. And it's divisible by 8. So then we continue to, is 32 divisible by 5? Nope. Is 32 divisible by 6? No. 32 divisible by 7? No. Is 32 divisible by 8? Yes. And notice here I'm already at the 8 that I had before. So that tells me that I finished all the calculations I need to make. These are the natural number factors of 32. So once you start repeating factors you found, that's how you know you're good to stop. So why don't you take a moment to pause the video and attempt finding all the natural numbers factors of 44 on your own, and then unpause to check your work. And you definitely, I think, would want a calculator handy for this part. So with this, I know naturally 1, the number itself, and 1 are always factors, so I'm going to write down 1, give it some space, going to write down 44. And then I'm just going to keep using my calculator. 42 divided by the next integer is 2, it does divide, specifically 22 times, so I write down those both as a factor pair. 44 then divided by 3, we see gives us decimals, so we don't count that. 44 divided by 4 works and gives us 11. 44 divided by 5, 44 divided by 6, and we're just going to keep going until we eventually start repeating some of the numbers, maybe at 11, who knows. 44 divided by the next number 7 gives us decimals, doesn't work. 44 divided by 8 doesn't work. 44 divided by 9 doesn't work. 44 divided by 10 doesn't work. 44 divided by 11. But notice we already had 11 in our list, so we've kind of gotten to the point where we're repeating terms, so we know that we don't have to keep going, because even if we kept going, the only new values we'd find are 11, 22, and 44, which we already have recorded. So those are the natural number factors of 44. And hopefully we can kind of see these factor pairs here. 4 times 11 is 44, 2 times 22 is 44, 1 times 44 is 44. So this is what I meant when the factors come in pairs. Now, one part of this class is looking back on mathematics, particularly before the modern age. That's the reason that we started with our historical numbers in our previous chapter. And for this, we're going to look at some divisibility rules. And it's very easy to think, well, we could just type it into our calculator and check like we just did, which is true. But remember, a calculator in terms of human history is a very recent invention. So for the majority of human existence, people were doing calculations without the aid of computers or other such technology. And as such, mathematicians who studied these things were able to find certain patterns that made evaluating divisibility of certain numbers a lot more efficient than just doing long division at each case. So this is why we're looking at these divisibility rules now, to kind of appreciate their historical context. So you can know a number is divisible by 2 if the last digit is 0, 2, 4, 6, or 8, or rephrase if the last digit is an even number. Now I think particularly this is very useful to know, so if you don't already have this memorized, I think this would be beneficial. That's how we can look at a number like 106 and automatically know it's even or divisible by 2 because the last digit is an even number. Okay. Now how do you know a number is divisible by 3? If the sum of the digits is divisible by 3. So what that means is if you have the number 123 and you want to know is it divisible by 3 and you don't want to go through long division or use our calculator, then what you would do by this rule is you would take each of the 3 digits and add them together. That's what it means by the sum of the digits. That would give us 6. Notice by adding the digits it gets you to a smaller number. So definitely 6 is divisible by 3. So the conclusion is, since the sum of the digits is divisible by 3, this implies the original number is divisible by 3. So this would definitely be a lot faster than going through the long division for each problem related to that. Now for 4, it's divisible by 4 if the last 2 digits are divisible by 4, so an example of that could be is 624 divisible by 4? Well, we could check using this rule by looking at the last 2 digits. This tells us to say this whole number is divisible by 4 if 24 is divisible by 4, which indeed 24 is divisible by 4. Which tells us 624 is divisible by 4. So that's what they mean by the last 2 digits. Now the next one that would be good to know is, you know a number is divisible by 5 if the last digit is a 0 or 5. 6, you know it's divisible by 6 if the number is both divisible by 3 by the rule and by 2. Now I'm going to say for 7 and 11, these rules, while interesting, are a bit complicated, so I wouldn't ask any divisibility rules based on the 7 or 11, so if you want you can just kind of cancel these out of your notes. So let's continue. 8 is divisible if the last 3 digits are divisible by 8. So kind of like the last two digits for 4, except now it's 3 digits. 9 is similar to 3. It's divisible by 9 if the sum of the digits is divisible by 9. 10 if the last digit is a 0, that's a good one to know. And then it's divisible by 12 if the number is divisible by 3 and 4. So that kind of lists out our ideas. Let's see this applied in our next example. It says decide whether 1875 is divisible by 5 and state the correct reasoning based on divisibility rules. Well, looking at the divisibility rules for 5, it says it's divisible by 5 if the last digit is a 0 or a 5. Looking at the last digit here, we see the last digit is actually a 5 in this case. So we would just say 1875 is divisible by 5 since the last digit is a 5. So we're just stating why this divisibility rule applies. Now our next example says state whether 156 is divisible by 12 and use correct reasoning. So in order to see if it's divisible by 12, we first have to check, is it divisible by 3 and is it divisible by 4? If both of these check out, then we know it's divisible by 12. So to check if it's divisible by 2, so 2 divides 156, this is our notation, our question. We look and the last digit is a 2. So that means that 2 does divide 156. Remember, this vertical bar means does divide. Next we need to check, oh, but that was, sorry, I said this for 2, but if we see for 12 it's divisible by 3 and 4, I think I was trying to check if it's divisible by 6. So while that's the correct reasoning for 2, that's not what the question asks, so let's go back and start correctly with is it divisible by 3. So is 156, can 3 divide into 156? Looking at our rule here, is the sum of the digits divisible by 3? So we take 1 plus 5 plus 6, and that would give us 12, and definitely 3 divides 12, which tells us that 156 is divisible by 3. Next, let's check does 4 divide into 156? So that rule is if the last two digits are divisible by 4. So the last two digits here are 56, so we'd have to ask ourselves, does 4 divide into 56? And in this case, if you need to use your calculator to support your reasoning, feel free to do so. 56 divided by 4 is perfectly divisible by 14, so that checks out. So we could say 56 is divisible by 4. That statement tells us 156 is divisible by 4. So to finish up our conclusion, is since 156 is divisible by 3 and 4, we know it's divisible by 12 by our divisibility rules. Now our next example asks us whether this large number is divisible by 9 and state our correct reasoning. Looking at our list, we know something is divisible by 9 if the sum of its digits is divisible by 9. So we would just set to adding all the digits together carefully, either by hand or with our calculator. And when we would do so, we would get the value 5 plus 6 plus 5 plus 4 plus 1 plus 2 plus 3, and we get 26. And 26 is not divisible by 5 perfectly, or sorry, by 9. This means the larger number, by result, is not divisible by 9. So that's how you would work with these divisibility rules. Now we're going to discuss what makes a number a prime number. So if we have a natural number that is larger than 1, that's a key phrase here, and the only factors it has is the number itself and 1, that is called a prime number. Some examples of prime numbers are 2, 3, 5, 7, and many more such examples. Now one thing to note is 2 is the only prime number that is even. All other even numbers are not prime because by definition they have 2 as a divisor. And to be a prime number you do need to be greater than 1. Now this definition breaks every natural number into either a prime number or not a prime number. And we've got a special word for when something is not prime. When something is not prime, we just call it a composite number. So examples of composite numbers are 4, 6, 9, 12, 15. All of these have factors that are different than the number and 1. For instance, 15 is divisible by 3, 5, 1, and 15. Notice it has 4 different natural number factors, whereas a prime number would only have 2 natural number factors, the number and itself. Now it's really important to recognize the prime numbers, so one thing I'd say is I am going to make sure this would be on any exam. It's not going to be listed on quizzes, so for our quizzes you'd want to make sure you have this close to hand, but you would definitely want to have written down somewhere the prime numbers that are under 100. So I have them listed out here for you. I recommend transcribing this somewhere where you'd have it close to hand for homework and future quizzes, because we'll need to reference which numbers are prime. Now one important thing to realize about prime numbers is their particular property in that every natural number can be expressed as a product of primes in a unique way. This is what's called a prime factorization. So specifically, notice 50 can be expressed as 5 times 10, and 50 can also be expressed as 2 times 25. But these are not prime factorizations because they're not made up of only prime numbers. For instance, 10 is not prime, 25 is not prime. There is only a single prime factorization of 50, and we can find it through something called a factor tree. So to start with the factor tree, you would write the number at the top, and then we would just list out the prime factors, and we're going to write out all the factors and keep breaking them down until we get down to only prime factors. So I might know off the top of my head that 50 can be divided by 2 25 times. Notice 2 is already a prime number, so this is not going to get broken down further, but 25 could be simplified into 5 times itself 5. But now if we look at our list of prime numbers, 5 is prime, as is this prime, so the bottom of our factor tree is only prime numbers. This tells me the prime factorization of 50 is 2 times 5 times 5, which could be rewritten as, since the 5s are multiplying by themselves twice, 2 times 5 squared. And notice when we calculate this, if we were to type this into our calculator, 2 times 5 times 5, we get 50 back, so that's a way you can always check your work. So this is the prime factorization of the number 50. And we found it by using our factor tree until we got down to all prime number factors. So let's continue this process to find the prime factorization of a few more examples. So let's go through this next example together, and then I'm going to ask you to use the pause activity for the next example just to go through it and practice it on your own before you see the solution. So if we're asked to find the key phrase prime factorization of 1460, what we would do there is we would take 1460 and we would start dividing it to find its factors, and here we might want to have our calculator. And one thing to note, everybody's factor tree might look different in the middle steps. For instance, with 1460, I could see somebody easily saying, well, I know it's divisible by 2. And their factor tree is going to start looking like this. But what if somebody else said, well, I know it's divisible by 10? That's also true. And what's going to happen is, based on how you start dividing it, the middle parts will be the same, but the prime factors that you get at the end are going to be exactly the same. So just remember, even if you do the middle steps different, based on the procedure, we're all going to get to the same final location. So for instance, let's start with the second step. If we found 1460 divided by 10, we know it's divisible by 10 because the last digit is a 0. Now our goal is to keep splitting these until we get down to only prime numbers, which is why keeping the list of prime numbers under 100 near you right now would be helpful. But 10 can be split into 2 and 5, which are both prime numbers, so those can stop. But for 146, I might say, well, I know it's even, so I know I can divide it by 2. And this is where we'll want to reference our list of prime numbers. See that 73 is one of our prime numbers under 100. So we've gotten to only prime numbers in the bottom of our list, which means the prime factorization of 1460 is, and you just write down how many times it appears. 2 appears twice. We have a 5, we have a 73, and we want to be able to recognize this if it was written as exponents. Repeated multiplication is an exponent, so 2 squared times 5 times 73. And that would be the prime factorization. And this is a really important concept to be comfortable with because our next ideas related to greatest common factor and least common multiple are all related to the prime factorization. So for our next example, we're asked to find the prime factorization of 285. So why don't you take a moment to attempt this on your own. So pause the video right now, work out this problem, and when you're ready to check your work, unpause, and you'll see the solution discussed. So if we're finding the prime factorization of 285, we could see that the last digit is a 5, so we could know that it's divisible by 5. Specifically, how is it divisible by 5? 57 times. Now we know 5 is a prime number, and if we were unsure about 57, we would just reference our earlier. And we see here 57 is not one of the prime numbers, so that could be broken down farther. Now if we're not sure what it's divisible by, we could just start trying things. It's not divisible by 2. Try it by 3. Notice we get a nice integer, so it is divisible by 3. This could be split into 3 and 19. Now if we're unsure whether, we know 3 is prime, but if we're not as sure about 19, just reference the list, and notice 19 is a prime number listed in our primes less than 100. So this prime factorization is complete, we just need to write it out. 285 is 3 times 5 times 19. And we can always check our work by taking 3 times 5 times 19 does give us 285 as expected. Next we're going to talk about greatest common factor. The greatest common factor of a group of natural numbers is the largest factor for all the numbers in the group. So it's not the largest factor of each number itself, but the larger factor that is common to the whole group. Now there's a few steps that we can follow, and we can always find the GCF in that case. Greatest common factor is often abbreviated GCF. Step 1, write out the prime factorization, what we just practiced, of each number in question. Once that's done, step 2 has us choose all primes that are keyword common to all the prime factorizations. With all of those common primes, you choose the least exponent that it has in any of the factorizations. We'll see this in an example. It's a little bit easier to see than to say. Step 3, you then form a product with all the numbers that you found in step 2, and that is the greatest common factor. So let's get started with this first example. Step 1 is to find the prime factorization of each number. Now we've been practicing prime factorizations for a bit now, so we're setting up the work, and I'd recommend that you pause the video now and then unpause to check your prime factorizations, and we'll talk about the next step from there. Now we know 54, since it ends in an even number, is divisible by 2, specifically 2 and 27. Now 2 is a prime number, so it can stop, but 27 can be split. Specifically, I might remember 27 is divisible by 3 9 times. Now 3 is a prime number, so it can stop, but 9 can be split into a 3 and a 3. That tells me the prime factorization of 54 is 2 times 3, 1, 2, 3. That would be 3 cubed. And you can always check 2 times 3 times 3 times 3, 54. Now 108 is also even, so we know it could get split into 2 and 54. 54 is also even, so it could be split by 2. Now 27 we just saw can be split into 3 and 9, which could be split in 3 and 3 again. And notice the ends of our factor tree are now all prime numbers, so we can write our prime factorization. 108 is 2 occurs 1, 2 times, so that's 2 squared, times 3 occurs 3 times, that's 3 cubed. Double checking this. And we get 2 squared times 3 cubed is 108. So now we finished step 1, now comes step 2. You would choose all primes that are common to both expressions. Do you see there's a 2 as a prime factor in both expressions? There is also a 3 that's common to both expressions. So that's what we mean by common, it appears in both. So we know the GCF is going to involve a 2 to some exponent times a 3 to some other exponent. We just have to decide what the exponent is, and that's where the second part comes. Choose the least exponent that it has in any factorization. So let's look at the exponents that appear on the 2's. Here there's no exponent written, and when there's no exponent written, that means there's an implied 1. So remember, no exponent written is an implied 1. Compare that to the other exponent on the 2. Which one is the least? That would be to the first power. So in this case, you could either write that it's to the first power, or if you want, you could just leave an implied 1 by not writing anything at all. Both of those are correct. Next, turn our attention to the 3. Notice the exponent on both factors of 3 is just 3. So in that case, the least is just the number itself. So our GCF is 2 times 3 times 3 times 3 times 3. The GCF is 54. And in this case, be able to recognize the GCF written out in the prime factorization or the numerical value itself, because 2 times 3 cubed is 54. That's exactly how we would represent 54. And the GCF in this case happens to be one of the digits itself, and that's because 54 divides into 108. 54 is a factor of itself, 54 is a factor of 108, and definitely there's no factor that's larger than 54 that is a factor to just both 54 and 108 itself. So that's a little trick. If you know one of the numbers divides into the other number, it would automatically be the GCF. So let's turn our attention now to 15 and 60. We would start step 1 over by writing the prime factorization of each. I think it's a good time for you to pause the video, attempt this on yourself, unpause to check your work. Here we know the factors of 15 are 3 and 5, both prime numbers. Now 60 I know is 2 divided by 30. Again, remember, you might have divided differently, but our prime numbers at the end will still be the same. The end of the tree are all prime numbers, so we can stop here. I'm going to write out the prime factorization. 15 is 3 times 5. And then 60 is 2 times 3. And actually 2 occurs twice, so that would be 2 squared times 3 times 5. And then for the GCF, remember, you only look at the prime factors that are common to both expressions. So look at the prime factorizations in both and think what numbers are common to both expressions. Do we see the 3 occurs as a prime factor both in the 15 and the 60, as does the 5. But the 2 does not. The 2 appears in the 60's prime factorization, but not in the 15. So the GCF is going to be 3 to some power times 5 to some other power. All that's left for us to figure out is the exponents. So you look at the exponents currently there, and remember you choose the least exponent possible. So for the 3, they both have just an implied 1, so the result would be the implied 1, which you could write or not write. And for the 5 as well, they both occur in both factorizations to 5 to the first power. So the GCF is 3 times 5, which is another way of expressing 15. And the process works for even larger numbers. So if we're finding the GCF of 360 and 2700, first step is to find the prime factorization. So we would start our factor trees. This is a good time to practice your prime factorizations. Why don't you pause the video, write out the prime factorizations, and unpause, and actually try to find the GCF as well. So why don't you complete the whole problem while it's paused, since we've seen it a few times, and then unpause to check your work. Okay, we know 360 is divisible by 10. Is divisible by 2 and 5, both primes. 6 is divisible by 6 in itself, but 6 is not a prime number. It could be split into 2 times 3, 2 times 3, and here we see the bottom of our factor trees are all prime numbers. Now for 2700, we could notice that 2700 having 2 zeros means it's divisible by 100. 100 is divisible by 10 in itself, which in both terms could factor to 2 and 5. 27 we've seen before factors 3 and 9, but 9 factors into 3 in itself. And then it's helpful to write the prime factorizations near each other. So we have 360 equals this, 2700 equals this, so let's count. In 360, we've got the factor of 2 appearing 3 times, so that's 2 cubed, times 3 appears twice, 3 squared. 5 appears once, that's just 5 to the implied first power. You can write it if you wish. For 2700, we've got 2 appearing twice, 2 squared, times 3 appears 1, 2, 3 times, so that's 3 cubed, times 5 appears twice, 5 to the second. So we've written out the prime factorizations. To find the GCF, you think what prime factors appear in both expressions. And here we see we've got a 2 to some power, a 3 to some power, a 5 to some power. So we know it's going to be 2 to something times 3 to something times 5 to something. How do you find the exponents? You look at the least exponent that occurs in either expression. So we've got a 2 to the third, and we have a 2 to the square. The least of those is the square, so this becomes 2 squared. For the 3, we've got a 3 squared and a 3 cubed. The least of those is the square, so the 3 also becomes squared. And for the 5, we've got the implied 1 and the exponent of 2. So the least exponent is just to the first power, the implied 1. So this is our GCF, but we could also find what this is in terms of actual number. So this is the prime factorization, but that is equal in our calculator to 2 times 2 times 3 times 3 times 5. The GCF is 180. So remember, these are both the same answers, just expressed in different ways. Next, we're going to discuss the least common multiple, sometimes abbreviated LCM. Now, in the least common multiple of a group of numbers, it is the smallest natural number that is a multiple of all the numbers in the group. So this is the somewhat tricky thing. Between greatest common factor and least common multiple of a set of numbers, you would think the word that has least would be the smallest, but that's actually not true, because the idea of multiple means something that's bigger than the number itself. For instance, we would say 30 is a multiple of 5, because 5 times 6 equals 30. So to be a multiple of a number means you're at least equal to the number, if not bigger. So when we're talking about least multiple, we're talking about the least number that's a multiple of all the items in the group. Whereas greatest common factor, to be a factor, you've got to be smaller than or at most equal to the number. So to be the greatest common factor, you've got to be something that's equal to or smaller, but for least common multiple, you've got to be something equal to or bigger. Now the steps for finding the least common multiple are somewhat similar to greatest common factor, but they deviate in a few key areas. The first step, they're in agreement, write out the prime factorization, just like we did for greatest common factor, same skill there. But once you have the prime factorization of each number, the difference comes to what they do with the exponents and what prime factors they keep. So for the least common multiple, you choose all primes, regardless of whether they're common to all the factorizations. Once you have all the primes, you choose the greatest exponent possible. So we can see this is quite a reverse from step 2 of the GCF. Multiply all these together and that becomes your least common multiple. So let's see this in action in our first example. So to find the least common multiple of 12 and 60, we begin the same way to find the factor trees here. Now 12 is 3 and 4, 3 is prime, 4 could be split into 2 and 2. 60 could be 5 and 12, but you could also start it by dividing it by 2 as well. 5 is prime, 12 could be split into 2 and 6. 6 is 2 and 3. So we would get the prime factorizations of 12 is that 2 occurs twice, and then it occurs multiplied by a single 3, so 2 squared times 3. 60 is, we see that we have 2 occurring twice along with a 3 and a 5. So that's going to be 2 squared times 3 times 5. Now for least common multiple, you don't only look at common factors that are primes, you look at any prime. So 2, 3, or 5 are all going to be part of our least common multiple. Still not sure what exponent. To determine the exponent, you look at the exponents that occur in either factorization, and you choose the largest one. Now for the 2, they both have the exponent 2, so we can't choose there, we're just stuck with the 2. For 3 as well, they both have the implied 1 as the exponent, as does 5. So we choose the greatest one that occurs in either, but in this case they're both to the exponent 1. So this is the least common multiple. If we wanted to figure out this value, we could by multiplying the expression. 2 times 2 times 3 times 5. Oops. And we would get 60. And there's a pattern that we can notice here. We don't need to because we can always follow these procedures to get the answer. But if we see the pattern, it might speed things up. Do you see that the least common multiple in this case happens to be one of the numbers? When the other number can be multiplied by a number to get you the other one, for instance 12 times 5 is 60, so 60 is a multiple of 12, then by definition the least common multiple would be the number 60 itself. So let's turn our attention to our next example to find the least common multiple of 135 and 280. Again, we would set to the task of finding the prime factorizations of each of these. While you take a moment to pause the video, find the prime factorizations, and attempt the problem that we just did on your own, following steps 1, 2, 3. Unpause to check your work. Now 135 ends in a 5, so we can know it's divisible by 5. We would get 5 and 27. 5 is prime. Now 27 can be split into 3 and 9, which can further be split into 3 and 3. 280 could be divisible by 10. 28 is divisible by 4. Remember, the intermediate steps might be different, but in the end, everybody should end up with the same prime factorization. So for 135, we get the following prime factors highlighted in yellow. For 280, we would get the following prime factors here. So we could write out their prime factorizations. 3 occurs 3 times here, so 3 cubed times 5. 280 occurs 1, 2, so 2 occurs 3 times. 3 doesn't occur at all, but 5 occurs once, as does 7. Now if we wanted to, remember you could always check your work. That definitely is 135, checking the next one. 280, so those are correct. Now to find the least common multiple from these, remember you write down any prime that ever occurred. So that means there's going to be a prime 2, prime 3, prime 5, prime 7. 2 times 3 times 5 times 7. Now we don't know the exponents yet. We have to find that occurred, and you would choose the least one of those. So in this case, 2 occurs to the cube. There's nothing else to compete with it, or the greatest one of those, sorry. So that would be 2 cubed would be the exponent here. Now for 3, that occurs only here as well, so there's no competition. It's also going to be 3 cubed. For 5 occurs in both cases just to the first power, so the greatest that we could choose is to the first power as well. And 7 occurs only once to the first power, so the greatest option is 7 itself. So that's the least common multiple. If we wanted to figure out what that number would be, we'd say 2 cubed times 3 cubed times 5 times 7, and we get 7,560. Would be the least common multiple of 135 and 280. Now we're going to go through one more example of this, and then we'll go through a few word problems related to our greatest common factor, least common multiple idea. So why don't you take a moment to attempt this next problem, complete it on your own. Least common multiple is 74 and 88. Remember that starts with a factor tree, and then finding the LCM based on the procedure listed before. So pause the video, unpause to check your work. Now 74 is divisible by 2. 37, if we're not sure if it's divisible, we would look at our list of primes. And looking at the list of primes under 100, we see that 37 is indeed a prime number. So this is our prime factorization there. 88 is divisible by 2. 44 is divisible by 2. 22 is divisible by 2. And here we've got all the prime factors of 88. So for least common multiple, you choose every prime that appears in either expression. So that would be 2, 3, 7. We've already got 2 and 11. But we don't know the exponent yet. We look back at the factorizations and we choose the greatest exponent that ever occurs for the least common multiple. 2 has an implied 1 and a cube. The greatest of those is the cube, so that's what we have as our exponent. Then we've got 3 to the first, no other 3, so we choose to the first power. I'm going to write my implied 1. We've got a 3 to the 7th power here. Oh, and sorry, 1 second, that is 37, not 3 times 7. So that should be 37. That should be 37. I was just writing that incorrectly. Okay, so that's the number 37. That occurs once, and 11 only occurs one time, so we've got that to the first power. So this is our least common multiple, and if we wanted to find its value, we could type in the expression that we got here. And the least common multiple is 3,256. Now in this section we have some word problems that are always related to the greatest common factor. Let's read through and kind of talk about why it's the greatest common factor, and then we'll go through and solve it just as we solved other greatest common factor problems. So it says that Terry has some pieces of 2x4 lumber. Some are 60 inches in length, others are 72 inches, so different sized pieces of lumber. All the lumber must be sawed into shorter pieces, and we want all the sawed pieces to be the same length. This gets us the idea of a common factor. Because all the boards that we saw, whether it's from the 60-inch board or the 72-inch board, we want the resulting pieces to be the same length. But the only reason we can do that is we've got common factors there. And we want to make sure there's no lumber left over. That, together with this, gives us our common factor idea. And when it says what's the longest such piece that we can make, where there's nothing left over and they're all the same size, this tells us we're looking at the greatest. So together we can kind of see where we're getting our greatest common factor. So this problem really boils down to finding the GCF of 60 and 72. Once we recognize this, it's no different than the mini problems we've done previously. We'd draw our prime factorizations of the two number, find the greatest common factor. So we have 60 is divisible by 5, 12, 5 is prime, 12 can be split into 2 and 6, 6 can be split into 2 and 3. We end when our factor tree has only prime numbers at the bottom, which we've got there. Now for 72, we have 72 is divisible by 2 and 36. 36 is divisible by 2 and 18. 18 is divisible by 2 and 9. 9 is 3 and 3. So our greatest common factors would be 60 is 2 appears twice, so that's a 2 squared. We've got a 3 once and a 5. 72 is 2 occurs 1, 2, 3 times, so that's 2 cubed. 3 occurs 1, 2 times, that's 3 squared. We can verify these. Great. So then the GCF, you choose only the primes that are common to both expressions. So only the 2 occurs in both, and the 3 occurs in both. Notice the 5 occurs in the first, but not the second. So the primes that we choose to make up the greatest common factor are 2 times 3. We exclude the 5 because it's not common here, but it is common here. Next, we choose the exponent. We know for greatest common factor, you choose the least exponent that occurs in each term. So the 2's got a square and a cube. The smallest of that would be square. The 3 has an implied first power and a second power. The smallest would be to the first. So that means our greatest common factor is really the number 12. 2 squared times 3. So if we cut each of the boards into 12-inch pieces, we'll have all 12-inch pieces, which is the largest factor that's common to both board lengths, and nothing will be left over if we assume we don't lose anything in the sawing process. So let's read through our next example. We have that a choral director needs to divide 180 men and 144 women into all male and all female singing groups, and we want each group to have the same number of people, and we want nobody left over. So this is our idea of our common factor. How can we make groups that are common to both numbers of people in the original groups? And the greatest comes from the largest number of that. So this tells us we're looking for the GCF of 180 and 144. Once we recognize that, we just start finding the prime factorizations of both. And then we're going to write those out here. And then write down our GCF, just as before. So we know 180 is divisible by 10. That would be 18 and 10. 10 is split 2 and 5. 18 could be split by 2 and 9. 9 is split by 3 and 3. We get down to all our prime factors. Now 144 is 12 and 12, I believe. You could also split it starting differently. Great. Now 12 can be split as 2 and 6. 2 and 6. 2 is prime, but 6 can be split further. So our prime factorizations of 144 is 2 occurs 1, 2, 3, 4 times. So that's 2 to the 4th times 3 occurs twice. That's 3 squared. We can verify that. 144. 180, we've got 2 occurs twice, so that's 2 squared. 3 occurs twice, that's 3 squared. 5 occurs once. We can verify that. 180 just as expected. Now greatest common factor, remember you choose the primes that occur in both that are common, so 2 is 1. 3 is 1. But although 5 occurs for 180, it does not occur for the 144. So 5 is not part of the GCF. So instead we've got 2 to some power times 3 to some power. We look at the exponents. We know we choose the least exponent possible. So between 4 and 2, we choose the least of 2. Remember, the LCM choose the greatest exponent. Greatest common factor choose the least exponent. So it's kind of swip-swapped. So for 2, we've got the highest exponent in both is 2. So the least of those is also 2. Which means our greatest common factor could be expressed as 2 squared times 3 squared, which is really the number 36. So if we split both groups into smaller groups of 36 members each, we will have the largest number of people in all the individual groups, where each group has the same number of people, and that's the largest such group. Now remember, at the end of all of our notes sections, we do have textbook homework assigned. It's listed here, so you'd want to go through the note packet and find the homework problems. All of these homework problems are odd intentionally, so that after you finish a problem, you can check your answer in the back of the book. Remember, if your question's incorrect and you have questions, you don't know how to correct it, you can send me a picture of your work and I'd be happy to give you feedback on how to correct it, and you can send that message either through Canvas message or our school email.